First, let's take a look at the physical model used to represent the ammonia molecule. It can be represented as follows. The representation on the left highlights the molecule atomic structure. The central atom is nitrogen, represented in blue, bound to 3 hydrogen atoms, represented in white. In this representation, we can see the shell and the electron on each atom. In this way, we can see that hydrogen and nitrogen share one valence electron each to form bonds. They are simple covalent bonds. In addition, the difference in electronegativity between hydrogen and nitrogen is 0.84, so this is also a polar bond. So nitrogen and hydrogen are linked by simple polar covalent bonds. The ammonia molecules has 8 valence electrons. In fact, the last nitrogen shell has 3 pairs of electrons shared with the 3 hydrogen atom and 1 pair of isolated electrons. And on the right, we can see the molecular representation in space. We can see that ammonia has a trigonal pyramidal shape, but if we take into account the lone electron pairs, ammonia actually has a distorted tetrahedron shape, as the unbound pair electrons applies a greater repulsive force, so it occupies more space. As a result, the angle between the bond is slightly less than a perfect tetrahedron at 107 degrees. Now we will see the atomic structure of each atom in our molecules. Hydrogen is the simplest element in existence. It consists of a single shell with 1 electron in the wall, 1 valence electrons. Its electronic configuration is 1s1. Nitrogen is made up of 7 electrons distributed in 2 shells with 5 valence electrons in each outer shell. Its electronic configuration is 1s2, 2s2, 2p3. There is a single electron in each suborbital for greater atomic stability. Now that we've seen the electron configuration of the 2 atoms, we can also represent the ammonia molecule with its orbital. The 3s orbital of hydrogen is easy to identify. In the case of the nitrogen, we have sp3 hybridization. In other words, the s and p orbitals have combined from 4 equivalent sp3 orbitals.
I will discuss about the position and periodic table. Firstly, we have nitrogen. Nitrogen is non-metal located in group 15. It has 7 atomic number and 5 electron valence in its outer shell. Its outer shell electron in the p subshell. Nitrogen can share electron to form a compound. Then we have hydrogen. Hydrogen does not fit neatly into any specific group, but it is in a group 1 and is not a metal. Hydrogen have 1 atomic number and 1 electron valence in its outer shell. Lastly, NH3. NH3 can form by the sharing of electrons between 1 nitrogen atom and 3 hydrogen atoms. Nitrogen contributes 3 electrons and each hydrogen contributes 1 electron, resulting in a total of 8 valence electrons in the compound. Then I will discuss about properties and benefits of the atom. For properties in NH3, if we look at the left side of the slide, nitrogen position in periodic table is located in group 15 and have 5 electron valence. Nitrogen trend in electronegativity is nitrogen is more electronegative compared to hydrogen. Electronegative trends to increase across period and decrease down groups. Nitrogen tendency to form covalent bonds is nitrogen forms 3 covalent bonds with 3 hydrogen atoms for achieving a more stable configuration. Then we look on the right side of the slide. The hydrogen position in periodic table is on the top of group 1 and it has 1 electron valence. Hydrogen trends in electronegativity is hydrogen is more electronegativity compared to nitrogen. Hydrogen tendency to form covalent bond by each hydrogen atoms forms a covalent bonds with a nitrogen, since hydrogen only needs 2 electron valence to fill up its electron valence. Then we will look at a pattern in ammonia. First, we have a covalent bonding, and second, we have polar molecule. For covalent bonding, its electrons are shared between nitrogen and hydrogen atoms. Nitrogen share electrons with each of the 3 hydrogen atoms. For polar molecule, due to the higher electronegativity of nitrogen compared to hydrogen, the ammonia molecule is a polar. The nitrogen atoms attract electrons more strongly, creating a partial negative charge on nitrogen and partial positive charge on the hydrogen atoms.
Ammonia is a molecule that consists of one nitrogen atom and three hydrogen atom. The type of chemical bonds in ammonia involves covalent bond. So the nitrogen atom in ammonia forms covalent bonds with the three hydrogen atoms. So in a covalent bonds, atoms share electron to give a more stable electron configuration. In the case of ammonia, nitrogen shares one electron with each of the three hydrogen atoms, resulting in the formation of three sigma bonds. So the sharing of electrons in covalent bonds allow each atom to achieve a full outer electron shell. So it's follow the octet rule for stability. As for nitrogen, which have 5 electrons in its outer shell, it will share 3 electrons with 3 hydrogen atoms, allowing it to attain a stable configuration with 8 electrons in its outer shell. So the covalent nature of the bonds in ammonia contributes to the molecule's overall stability and structural integrity. To summarize, ammonia is held together by covalent bonds, specifically sigma bonds, which form through the sharing of electrons between the nitrogen and hydrogen atoms in the molecule. The bonding in ammonia, which involves covalent bonds between nitrogen and hydrogen atoms, significantly influence its properties and behavior. So here's how. First is polarity. The ammonia molecule is polar due to the significant difference in electronegativity between nitrogen and hydrogen. Nitrogen is more electronegative, meaning it attracts electrons more strongly. So as a result, the shared electrons are closer to the nitrogen atom, creating a partial negative charge on nitrogen and partial positive charge on the hydrogen atoms. So this polarity contributes to ammonia's ability to form hydrogen bonds and affects its interaction with other molecules. So the second one is hydrogen bonding. So the polar nature of ammonia allows it to engage in hydrogen bonding. The lone pair of electrons on the nitrogen atom can form hydrogen bonds with other molecules or ions containing hydrogen. Hydrogen bonding contributes to the higher boiling and melting point of ammonia compared to non-polar molecules of similar size. Next is boiling and melting points. So ammonia has relatively high boiling and melting points compared to similar sized non-polar molecules. This is because the presence of hydrogen bonding between ammonia molecules. So the hydrogen bonds require more energy to break, which lead to higher temperatures required for changes in state. On the other hand is solubility. So ammonia is highly soluble in water, primarily due to its ability to form hydrogen bonds with water molecules. So the polarity of ammonia molecule allow it to interact with the polar water molecules, which lead to the dissolution of ammonia in water. Next is conductivity. Ammonia in its pure form is a poor conductor of electricity because it does not contain ions. However, when it dissolves in water, ammonia have more ammonium ions and hydroxide ions. So, due to the presence of ions in solution, it allows for electrical conductivity. Next is its shape and geometry. So the ammonia molecule has a trigonal pyramidal shape with a lone pair of electrons on nitrogen, which creating a distorted tetrahedral arrangement. So this geometry affects the molecule's overall structure, and it also influence its reactivity in various chemical reactions. The last one is reactivity. So the covalent bonds in ammonia confer a certain stability to the molecule, but the lone pair on nitrogen makes it capable of participating in various chemical reactions. So ammonia can act as a Lewis base by donating its lone pair of electrons in reaction with Lewis acids.
I will discuss about real-world application. For question number 1, real-world application of ammonia is fertilizers production. Ammonia is a key component in the production of nitrogen-based fertilizers. It serves as a source of nitrogen and essential nutrient for plant growth. For example of its application is farmer use ammonia-based fertilizers to enhance soil fertility, promote crop growth, and increase agricultural productivity. For the second question, the properties that contribute in ammonia to the industry and real life. It is a basicity. Ammonia is a weak base readily accepting a proton to form ammonium ions. For example of application is its basic nature makes ammonia useful in pH control as a cleaning agent due to its ability to neutralize acids and in a various chemical processes where control basicity is required.
So the ammonia molecule is widely used in the explosive industry. For example, it's used for create tunnels. To do this, it must be transformed into ammonium nitrate by bubbling in citric acid. One of the properties that make it interesting for this application is its solubility in water. Ammonium nitrate dissolves in water to form NH4 plus and NO3 minus, which are ionic molecules relatively small size. Because of the ionic nature, the cation attracts water molecule via the oxygen atom holding the negative partial charge, and the anion via the hydrogen atom holding the positive partial charge, which favors their solubility into water. So what's more, it's also stable molecules that can be withstand shocks and high temperature with a certain limit. This is important in this field because it ensures the safety. The molecule stability depends from the type of bond it forms. So cation and anions have ionic bonds, and the atom inside have polar covalent bonds. This type of bond are quite strong and therefore require significant dissociation energy to break. So finally, the last property I'm going to mention is that ammonium nitrate is an oxidizing agent. Indeed, the presence of oxygen atom plays the role of oxidizer. Coupled with fuels such as, for example, oil, and given a sufficient amount of energy, it can be demonstrated its performance as an explosive product.
Ammonia is a compound that consists of 1 nitrogen atom and 3 hydrogen atoms. While ammonia itself is not directly used in the petroleum industry, so its properties make it valuable in various processes and applications within the industry. So here are the several ways in which ammonia properties contribute to the petroleum industry. So first is as a catalyst in hydrocracking and hydrotreating. So ammonia is used as a catalyst in hydrocracking and hydrotreating processes. So these processes involve breaking down large hydrocarbons into smaller and more valuable products and removing impurities respectively. So the presence of ammonia as a catalyst helps enhance the efficiency of these reactions. Next, ammonia also involved in desulfurization processes in the petroleum industry. So when crude oil or natural gas contains sulfur compounds, they need to be removed to meet environmental standards and to prevent corrosions. So here is where ammonia is used in gas sweetening processes to react with sulfur containing compounds, forming non-corrosive products that can be easily separated. Next is neutralizing acidic components. So ammonia can be used to neutralize acidic components in certain processes within the petroleum industry. This is relevant in situations where acidity needs to be controlled to prevent corrosion or unwanted reactions. So, to conclude, while ammonia itself is not a primary product of the petroleum industry, its unique properties and versatile applications make it an essential component in various processes and contribute significantly to the overall efficiency and sustainability of the industry.